Hello everyone, my name is Kirill Nekludov, and in this video I would like to tell you about the continuity equation. For those who don't know, the continuity equation is the foundation of the modern image generative models. But in this video, instead of the applications, I would like to tell you about the intuition behind this equation and the sketch of its proof. Let's say we are in a garden during the cherry blossom season. The petals of the cherry tree fall silently on the surface of the stream and are carried away by the water flow. We can start wondering, how does the water flow shapes the evolution of the petals? Why does some places have more petals and some places have less? To start even asking these questions, let me introduce some notation. We're going to denote as xti the coordinate of the ith petal at time t. Vt of x is going to be our vector field or the water flow at point x and time t. Qt of x is going to be the density of the petals at point x and time t. And just as a quick reminder, the density is such a function that if we take the integral of this function over some area omega, we'll get the portion of petals in omega. And the question we want to ask is how the density of petals changes in time, or what's the time derivative of the function qt of x with respect to t. But it's not really clear how to even start answering this question. So instead of this, let's try to answer something simpler, something that we know how to answer. For instance, for a single petal, we know that its coordinate changes at time according to the following differential equation. So the trajectory, the time derivative of the trajectory has to be equal to the vector field at this point. Even for many petals, we can say that we know how the average coordinate changes in time. Indeed, the time derivative is a linear operation, so we just put it inside our sum, and we get the average over the vector fields at these points. If we can answer this question about the coordinate or the average coordinate, then maybe we can answer this question about any function. Let's say we evaluate some function phi on every petal, like here on the image, and then we ask, how does the average of this function phi changes in time? So let's try to answer this question instead of answering how does the density changes in time. One way to go from this expression, the time derivative of the average value of function phi, is like a slide downhill. Indeed, if I see a derivative, I can just take this derivative. So let's just take the time derivative of the function phi, and just by the chain rule, we'll get the inner product of the gradient of phi and the time change dxti dt of every single petal, right? Then, of course, we use our knowledge about the vector field, because every single petal follows the vector field, so the time derivative of our coordinates equals to the vector field. And then we can say that for a large number of petals, our expression for n capital going to infinity actually goes to, in the limit, it goes to the expectation of this value with respect to the distribution of petals, which is defined by the density qt of x. Another way to go about this expression is to first climb uphill. In a way, we can wonder what was the previous form of this expression. And we can say that, let's say that this is an empirical estimate of the corresponding mathematical expectation. So in other words, we can just take the limit first. We can set n capital to infinity and then we'll get that this is the time derivative of the following mathematical expectation. And from there, we can go downhill once again. I see the derivative, I take the derivative. So the expectation is simply an integral, and we can put this derivative inside the integral and get the following expression. So this is the integral of the derivative of our density function multiplied by the function phi of x. From the previous two slides, we get two forms of the following expression. Indeed, one way to go from here is this integral, and another way to go from here is another integral, and they have to be equal. This is called the continuity equation, the weak continuity equation. And the mind-blowing part about this is that it holds for any function phi of x. Indeed, in the very beginning, we said that we're gonna choose some random function phi of x without any assumptions. Of course, I'm skipping a lot of mathematical assumptions because I'm just giving a sketch of the proof, but it's a very wide class of functions that can be in here, and this equation holds for any of them. If something holds for any phi of x, it's a good idea to try to get rid of this phi of x. So let's take the right integral, the integral on the right-hand side by parts. We'll get the following expression, and now we can move everything to one side and group the terms, so we have phi of x multiplied by this one bracket that equals to 0. Once again, if phi of x can be anything, then we see that the expression in brackets has to be 0. Otherwise, I could choose such phi of x that the entire integral is not 0. And voila, this is the pointwise continuity equation. Maybe you've seen it before in this form. One quick note is that the operator here that I've been using is called the divergence, and this is just a sum of derivative vi over dxi, and that's why it makes a lot of sense, and it's very intuitive to write it down as an inner product. After we have the result, I suggest you to look back, which is a very important part of both your studies and research. And while looking back, I suggest you to try to answer yourself the following questions. For example, what's the difference between the continuity equation in its weak form and the pointwise continuity equation? How does one relate to another? Or what if the density is stationary? So if the time derivative of the density is 0, can the vector field be non-zero, or does it somehow restrict the family of vector fields? Or does the change of density uniquely define the vector field, or does it happen in the opposite direction? Trying to answer these questions yourself will help you to deepen your understanding of the continuity equation and will help you to use it in the future. And that's it. That's the end of the video. Good luck in your research.